So the L'Hopital's rule can be used for indeterminate form. That usual way we are not able to simplify, then we apply or try the L'Hopital's rule that differentiates the top and bottom separately. Right? Be careful that we do them separately. Different as what we deal with quotient, right? We treat it separately as the ratio of two functions. It's not the chain rule that applies that treat it as a whole as a function, but we treat them as two separate functions for the L'Hopital's rule to find limit. Right, just that need to be careful. Right? Then we see the next example of limit x approaches to infinity of natural log of x over x to the second. Not second, to the higher power. Right, this limit, we don't have other ways to do, right? When we evaluate it, that is natural log of infinity, which is infinity. The exponential, not exponential, this is polynomial, right? That is also yields to infinity. So that is indeterminate form of infinity over infinity. Then we could apply the L'Hopital's rule. Such we do is differentiate of the numerator, that is 1 over x, denominator is 5x to the 4th. Right, from that we can simplify. That 1 over x divided by 5x to the 4th, it is 1 over x times 1 over 5x to the 4th. That is 1 over 5x to the 5th power. Right, that has still the higher power on the denominator with numerator as constant. Scalar doesn't matter what it is, that is still a 0. Right, if you want to show steps, you could say that equals 1 over 5 times infinity to the 5th power, which is still infinity, that give a 0 at the end. Let's see the next question. X squared over e to the 2x. Which indeed, right, no doubt that polynomial goes to infinity as x goes to infinity. Exponential function with positive power goes to infinity also when x goes to infinity. Right? So that is the indeterminate form. Of infinity over infinity, we can apply the L'Hopital's rule. That well, it is limit x approaches to infinity. The derivative of top, that's 2x. Derivative of bottom, that's e to the 2x times 2. We could cancel out the 2, that's x over e to the 2x. But when we observe this thing, it's nothing else similar as that. Polynomial and exponential function both goes to infinity. Still have the indeterminate form. Well, which L'Hopital rules say if the ratio of two functions is indeterminate, then we find the ratio of the derivative of them. Right? That's what the L'Hopital rules say. Doesn't say it can only apply once. It can apply many times as long as the condition of indeterminate format satisfies. That we have x over e to the 2x is infinity over infinity. That's an indeterminate form. So we can also apply the L'Hopital's rule to this new function. we get the derivative of top is 1, the derivative of bottom is 2e to the 2x. Which in this case, right, e to the 2x goes to infinity as x goes to infinity. And 2 times infinity is still infinity. That's this thing at the end has a limit of 0. Right? So we see that, well, in this we apply the L'Hopital's rule, but the result for first derivative we get a ratio that is still in determinate form. Then we can apply the L'Hopital's rule again, right, to see what will give us. Until it is not indeterminate, that means we're not getting 0 over 0, we're not getting infinity over infinity, we have constant over infinity in this case, then we are not able to apply the L'Hopital's rule. Right? L'Hopital's rule only be applied once we have the indeterminate form. Why 0 positive is because natural log only takes positive numbers. Even for the 0, if it's on the positive side, it will yield to a negative infinity. If you remember the graph of natural log, that is this format. Right? We'll have the vertical asymptote when it's on the positive 0 side, which is the vertical asymptote on the positive 0 side. And to be special, right? So that is the format of indeterminate again. Which is the format of 0 times infinity, right? It's actually negative infinity anyway, but that's still somehow the infinity. So what we can deal with that is 0 times infinity. We don't have L'Hopital's rule for multiplication, but what we can do is the two products, right? X is one term, well, natural log x is another part. That x is kind of easier to be flipped. Right? If we have a product, we can flip in one of the format or part into the denominator to make it as a ratio. In that case, we get, well, the numerator is negative infinity, the denominator is 1 over 0, that's also an infinity. Right, then we can apply the L'Hopital's rule to that. We get 1 over x as the natural log, we get negative 1 over x squared as the denominator. Simplify a little. 1 over x times negative x squared, we get a negative x. Oh, we flip the bottom, that's negative x squared. Negative x squared over x is negative x. Then the 0 applied to it, that will be negative, but a little positive of 0, but it's still a 0. And no matter how small or how positive or negative the 0 is, that is still the 0, right, in that case. So we get it is equal 0. We just, for the product as indeterminate form, we need to simplify to a ratio, right, to a quotient, then able to apply the L'Hopital's rule since it is an indeterminate form we have. form for x approaches to pi over 2. Secant is one of a cosine that cosine yields to 0. So secant, if you remember the graph of secant, that is this type of curve, -1 actually. But it has a vertical asymptote at pi over 2. Also tangent is similarly, right, but not similarly, a sine over cosine that has a period of pi, and for every pi over 2, for every pi has a gap of starting initially at pi over 2, it has a vertical asymptote, and so on. Right, so both of them are infinity over minus infinity is the indeterminate form. Right, for them, we actually kind of don't know what to do, right? That secant minus tangent, what can we deal with the secant minus tangent? Our purpose is to make them into ratio, so maybe what we can do is convert. Right, use trig property to convert. If you remember the trig property, right, that sine, cosine, tangent, cotangent, y in the middle, secant, cosecant, that they are ratio in the diagonal, reciprocals in the diagonal, and the ratio is next to the same side following, equals whatever it is, right? So we have that discussed in our review section, right, the first section, that secant is 1 over cosine, tangent is sine over cosine, that this limit can be applied to pi over 2 as 1 minus sine x over cosine x. Now this one, when we attach in pi over 2, we get 1 minus 1 is a 0, we get cosine of pi over 2 is also a 0. That we can see it is indeterminate form of 0 over 0, then we can apply the L'Hopital's rule. Derivative of sine is cosine. Derivative of cosine is negative sine. Simplify a little. We get cosine x over sine x. If you want, you could change that to cotangent, but keep that in ratio, that's also fine. What we can do is try to evaluate it. No problem that we get a 0 over 1. Right, 0 over 1, that is the format of 0. So secant x minus tangent x as x approaches to pi over 2, we get the value of 0. Then next we'll see some special thing. Right, for the limit as x approaches to 0 as x to the x, we have special way of exponent, right? That is the 0 to the 0 of the indeterminate form. Once we get the exponents, right, we are able to make that as a coefficient, only we have the logarithmic as an 8. Right? If we are kind of familiar with it already, we have seen couple questions about logarithmic SN8 to find the derivatives. But the basic property is the idea that the exponent convert to coefficient, then one thing could be taken to the denominator, then we are able to do the question. Right, so to start with that, we're starting with let y equal the limit. Right, then we could apply the natural log to it on both sides. And the natural log of the limit is the limit of natural log. Right, that is the initial steps of how we do the exponential part of indeterminate, not only 0 to the 0 as indeterminate or the format of 1 to the infinity as indeterminate, we also do this similar way. So from that we can get, we're evaluating the x approaches to 0, that x times natural log of x. This one actually we had seen already, right? That we get this one is a indeterminate form that is 0 times infinity. So we can do is flip one of the formats to the denominator. That we will get is 1 over x. That we'll get to apply the L'Hopital's rule, right? That is the format of infinity over infinity. Limit x approaches to 0 positive. That's 1 over x over negative 1 over x squared. That's negative x, which is a 0. But we have the result of 0, but that is our ln y. So we can write it more clear that ln y equal to 0. Then y equals the limit of x approaches to 0 positive x to the x is e to the 0, that is 1. Well, we apply the inverse function to evaluate the y. The y should be e to the 0, which the y is, if you write more clear, right? The y should be e to the 0 equal 1, not writing them in one step. Hence, what y is the limit of x approaches to 0 positive, and from the right as x, so to the x power is 1. If you want to write in one line, you could say y equals this thing equal e to the 0 equal 1, or two lines together, doesn't matter what to do. Right? Let's just be clear of what we're doing. Right, so in pre-calculus, I believe something you have seen before about the compound interest, right? Principal times that 1 plus ratio to the how many over n actually. Right, the compounded certain years, compound interest of t years, that interest rate is r, compounded n times per year. Right, that's the formula for compound interest. And when you say, well, if we compound infinitely, which means not even every second, but every moment, right? It is a compounded interest that we have, then our one plus r over n to the nt will yields to e to the rt. Right? Since the t is same, what it means is 1 plus r over n to the n will yields to e to the r as n goes to infinity. Right? That is the compound infinitely. Right? What I believe that was the thing you have seen in your pre-calculus. Right? One thing we will see here is 1 plus r over n to the n as n goes to infinity is e to the r. Right? So as n is the number of compounded and r is the interest rate. Right? If you put n as infinity here, you will see that it is the format of 1 plus 0 to the infinity, that is 1 to the infinity. Right? We yield to the form of that. Well, which 1 to the infinity is not 1, that is the indeterminate form. That is what we've seen in pre-calculus, they r should be equal. Then let's see, right? Find the limit to verify of 1 plus our constant, just say a over x to the x. Right, since that is exponential format, what we can do is apply the natural log. Right, so the same way as we do for last question, indeterminate of this format, we could let y equals the limit right, then the natural log of y will be natural log of the limit or could be limit of natural log. Right, that thing is exponent could be taken to the front. That we can evaluate as the format, which is infinity times natural log of 1 plus a little thing goes to 0, that's natural log of 1, which is a 0. Right, therefore, that is also an indeterminate form. Right, this one is an indeterminate form of 1, whatever it is. We just to the infinity, that's we take natural log and we get the format of infinity times 0. What we can do is flip that down. Natural log of 1 plus a over x over e 1 over x. Right, from that we actually have the format of 0 over 0. Since we flip the infinity to the bottom, we get 0. Then we can apply the L'Hopital's rule. The denominator, that's negative 1 over x squared. The numerator is 1 over 1 plus a over x times the derivative of that is negative a over x squared. Right. What we can do is cancel out the x squared and the negative sign. Right, if you want to see, that is the limit x approaches to infinity, 1 over 1 plus a over x times negative a over x squared times the negative x squared, which that cancel, that's 1 plus a over x, and the numerator is a. Right, so that's a over 1 plus 0 equals a. And to the top, what we get is y, or ln y we defined. Ln of y equals a. Right, so y equals the limit of x approaches to infinity, 1 plus a over x to the x, equals e to the a. Right, so that is 4 steps to show that from the compounded, finite compounded interest as to the infinite compounded interest. Right, that is what's the thing you didn't see in your pre-calculus. And in the middle was the bridge here, how it leads to this one into e to the a. Right, so this one is hard enough, and we see the most of the type of the L'Hopital's rule. Something, well, is still not that hard, but maybe you will see some more questions in your homework, and they may get a little trickier, but will not be as hard as this one, or will not be harder than this one. Right, so in conclusion, I have the infinite of infinity, 0 over 0, we have infinity minus infinity, we have 0 times infinity. This thing, these two, right, could be just directly apply the L'Hopital's rule. The third one we maybe can use into a fraction, then we can apply the L'Hopital's rule. This one, 0 times infinity, we change 1 into fraction, change 1 to the denominator, right, or the first or the second one down to the denominator, then we get the format of indeterminate ratios, fractions. And 0 to the 0 or 1 to the infinity, these two we apply the set to y and we apply the natural log to them, right, as an 8 to make the exponent back to the product. Then product can be a quotient. Right, so everything we need already. Then the 4.6 is the section of a summary of curve sketching. A summary of curve sketching. Right, so given a function to sketch on f of x, the first thing we need to take care of is domain. Right, then the x and the y intersect. Vertical and the horizontal asymptotes. Right, that was the view in the field in pre-calculus. Right, we have domain, x, y intercepts, vertical, horizontal asymptotes, and pre-calc say, well, together with maybe some other points, together we get a rough graph. Right, then for more accurate graph, what we had seen was the increasing and decreasing interval. Relative extrema. Then the next is concavity intervals and the point of inflection. We'll see the shape of increase, decrease, and concave up, concave down for the function. Then finally, we are able to tell the range of the function. Well, we get not a rough graph, but from that we get an accurate graph to use all the information that we're able to get the range right from that. So that is the full step. I just follow the steps: domain, xy intercept, vertical, horizontal asymptotes, increase, decrease interval, relative extrema, concave up, concave down, interval and point of inflection, finally the range of the curve, that we are able to get the accurate curve, accurate graph. So let's see how we do that. Sketch f of x equals 2x squared minus 9 over x squared minus 4. Right, so let's see how we do that, right? They told me very long steps. The first step is to find the domain. This thing cannot be simplified. We get x minus 3x plus 3x minus 2x plus 2 on the top and bottom. That domain is everything, but just cannot be negative 2 and the 2. Right, that's for sure of what it is. Right, then what we need is the second step is the x-intercept. Right, so x-intercept to let f of x equal to 0. I'll write the steps into the right side and the conclusion on the left side to be accurate. Right, then we get is the numerator part. To be 0. Right, and the y-intercept is the value f of 0, that is twice of 0 minus 9 over 0 minus 4, that is 18 over 4, 9/2. Right, so we get x-intercept negative 3, 0, 3, 0. Y-intercept 0, 9 over 2. Right, the second step to find x and y-intercept. The third thing is the asymptotes. We have our vertical asymptote, that is the denominator equal to 0. Right, since nothing can be simplified, the horizontal asymptote, you can apply the limit to it, but as rational function you don't have to. Just say, well, since we have same coefficient, that leading coefficients ratio will be the horizontal asymptote, the y equal to. So we have vertical asymptote, x equal negative 2, x equal 2. Horizontal asymptote, that is the line at y equals 2. Right, then to find the next step is for the increasing, decreasing, find the relative extrema. Right, we need more space, right? Hopefully this one is good enough. So first derivative, square minus 4 to the second power u prime 4x, x squared minus 4, minus v prime 2x, 2x squared minus 18. That's 4x to the third minus 16x, minus 4x to the third plus 36x, which is 20x. Right. F prime of x is 20x over x squared minus 4 to the second power. Right, that maybe we seal the thing on the left. Of course, when you do the question, since I don't have space, I just do steps and put the result on the left. When you do your question, you just use your paper to write everything together, right? Not only the results, but the steps also with it. That will be more appropriate. And for the critical number, is f prime of x equals 0 or f prime of x undefined? F prime of x equal to 0, that's numerator equal to 0. F prime of undefined, that's x squared minus 4 equals 0, which is not in our domain, so ruled out. Right, we have critical number is at 0, and we already evaluate the 0 now over 2 is our function, at our point, so we just need to see, right, the increasing decreasing interval. Interval test value for the sign of f prime and for the sign for the shape of our f. That is negative infinity to negative 2, negative 2 to 0, by 0 to 2 and 2 to infinity for pieces. Test value we can put maybe negative 3 in, negative 1, 1 and the 3, but consider the f prime of x, right? This bottom is always positive. If the top is positive, then the function has derivative positive. If negative, then negative. Right, what we have is just negative 3 times 20, that's negative. Negative 1 is also negative, positive, and a positive. Right, so we have increase, not increase. We have decrease, decrease, or we just put in a shape. Right? Decrease, decrease, increase, increase. And from decrease to increase, the point 0 now over 2 is our relative minimum. Right, so we can draw a small table here from negative infinity to negative 2, negative 2 to 0, 0 to 2, and 2 to infinity. We get decrease and increase for our function. And we have the relative minimum is the point 0.912. Right, that's we get from the first derivative. And to do the second derivative, f double prime, x squared minus 4 to the fourth power u prime times v minus v prime times u. We're able to cancel out one of that. That's 20 x squared minus 4 minus 480x squared. That is 20, well, that's negative 60 x to the second minus a. Alright, so for f double prime, which is this shape, so we can see that that is all positive, all negative on the numerator. That will find the possible point of inflection and then follow.